Hi guys, welcome back to the channel. In this video we are going to discuss the concept of multiplexer as universal logic. So we already discussed in the previous video that is multiplexer is a universal logic. We can build any of the logic we want with the help of the multiplexer. So this is the combination circuit. So let's get started. So let's get started with an example. So this is the example one. So you are seeing there that they have given a truth table. So even though they did not give the truth table, they can give in the simple SOP format in the terms of min terms they can give, like f is equals to sigma 0237. So we can fill that simply in the truth table. So after filling that, this is the truth table. So if you observe clearly, there are total 3 variables included here because they have gone up to the biggest term in this is 7. So 7th min term. So from that we can confirm that it has 3 variables A, B, C. So if you observe, we can implement this with the help of the multiplexer. So if you see, we have to use 8x1 multiplexer because there are 3 variables here is there. So for that we have to have 3 select lines. So I am taking the 8x1 multiplexer. So as you can see over there, this is the first method that we are going to implement the logic function with the help of multiplexer. So there we have took the 8,000 multiplexer because we have 3 variables A, B, C. So those 3 variables directly I took in the select lines, and the remaining all the outputs, that is 1, 0, 1, 1, 1, 0001. That all the outputs means the inputs here in this case I am taking in the input line. So if you are observing, suppose if you pass ABC as 0, 0, 0, then what we are going to select, that is D0. What is D0? 1. So that is the simple thing that we can say. That likewise we can select any of the input we want. The input only will be sent into the output. Suppose if you are sending ABC as 1, 1, 1, that output would be 1 because that is D7. Simply we can say from the line position also. So that's the not matter. So this first method is not efficient, and this requires much more higher multiplexers because we have n variables. So see down that is the equations. So suppose if you have n variables, we have to have n select lines for this method. If you are observing direct process, but this is the direct process. So example, in this case only we have 3 variables A, B, C. We are going to use 8x1 multiplexer. But we have the second method, that the very simple method, that is if you are using the 3 variables, then you should use the n-1, means the 2 select lines only. So that's the simple method. So let's wait for the second method. That's also will be discussed in this video only. That is very important for the solving of any of the logic gate. So this is the reason that I have kept in before this example, to differentiate between or 2 methods, to show the identification of 2 methods. So what if I say we only require n-1 select lines to perform any of the Boolean algebra, that Boolean expression that they have given. So that can be performed with the help of the second method. So now I will discuss the second method. Before that, let's see some statement here. So a Boolean function with n variables can be implemented with only n-1 select lines. So now only we discussed a Boolean variable with n select lines would be having n variables. So this is that is the first method, that is requires many more select lines and many more inputs. But this is the second method we can also implement in this method. If you observe, so n variables, so n-1 select lines and 3 variables. So example, that is 3 variables means two select lines there is. So 4x1 multiplexer can be used for the implementation of that. So you might think this video is based on universal gate of multiplexer, then we are discussing these all and all concepts. So basically the second method is very important for solving any of the logic gates. So before understanding all the logic gates, we need to understand the concept before that. So this is the concept. So this is the second method that is very important for solving all the logic gates. So that is the reason why that this example that I have kept it in before in. So if you observe, I am taking 4x1 multiplexer because we have 3 variables. So we can have 2 select lines because that's the second method. So as we are observing in the second method, so I have took the same example that I also previously shown. So with the help of previous method already we saw. So suppose if you observe here, so we have 2 variables, 2 variable lines, but we have 3 variables in the truth table, but we are taking 2 select lines only. So first we need to have the line wise. Suppose we have 3 variables as A, B, C. So A, B should be selected as select lines, or the represented as select lines. So if you are observing there, the A, B is represented as select lines. Then where is C? So then we need to represent C as input lines only. So if you observe, we need to compare C and F. Then we need to write all the expressions according to the C in the input lines. So if you observe, if you compare C and F, so you can observe that if C is 0, F is 1. If F is 1, C is 0. So that is the condition. So simply we can say F is equals to C bar or C bar is equals to F. So that is the reason that I am kept in the first one D not as C bar, because if you consider the first AB conditions, first two cases, that is the M1 and M2 positions, if you consider both are zeros, so AB is 0, so that is the reason. So I am sending 0 0, I am fixing AB as 0 0, then I am comparing C and F. That's the condition that I am coming. So the condition is F is equals to C bar, so D naught will be C bar. So for the next condition, that is D1, so for that we are going to pass AB as 0 1. So see the multiplexer, 4 cross multiplexer, we are going to just in the place of AB we are going to pass 0 1. So because that is the next two cases, right? So if you consider next 0 1 as AB two conditions, you have to compare C and F. If you consider C and F doesn't change for the two conditions, so that is known as F is equals to 1. So comparing means we are to the main output is F only, so we are going to have F in terms of C. So that is the main thing that you should remember or agree. So if you consider F in both cases would be 1, so we have to include the D1 as 1. I hope you are understanding this. The third condition, if you observe over there, so the F and C you have to compare. So AB is fixed, that is 1 0. So AB you have to pass 1 and 0. So if you observe F only, that is 0. 0 is not changing at all for the two conditions. C is changing. So don't if F's are both 1. So don't F's are both 1 means F is equals to 1 only. If F's are both 0, so take F 0 only. If it is somewhat similar to C, then take in terms of C, otherwise don't take. So first C, so F and C have some similarities, so that's why we took F is equals to C bar. If F and both are C, means F and C are same, then F is equals to C, that condition we can take, that is the last condition. But in this case F is only 0, so that is the condition we are going to follow, that F is equals to 0. That means in this case D2 is equals to 0 when AB is 1 0. And finally, if you consider in this table, the last two conditions matched exactly F and C. So the final output, the F is equals to C. So you can also observe in the 4 cross 1 multiplexer that we are sending A and B as 1 1. So final output would be selecting the last D3, that is C in this case. So remember these cases, we are going to apply all these cases while we are implementing the MUX. While we are implementing the logic gates with the help of the 2 cross 1 multiplexer. So this is the important concept, that is the second method. So remember this only. So first method is not that much step, but this is the efficient method, because for n-1 select lines only we are required for these situations. I hope you understood the concept behind that. But before going to implement the logic gates, we are going to see some second example so that you can boost yourself. So if you observe, they have given the minterms, that is these conditions. So they have gone up to 15. So by seeing that we can able to observe 15. So means total we have total 16 terms. So for this condition we have total 4 variables A, B, C, D. That is the condition we have to identify. So according to the truth table, I have filled all the minterms in the truth table that you are seeing, that is minterms from M0 to M15, because we have total 16 terms. So fill that is 1, 3, 6, 9, 12, 14, 15 in the truth table, that is in the positions 1. So we have truth table now. Remaining places we can fill with zeros. So I have left a column also. So in this case we have total 4 variables, that is A, B, C, D. Actually according to the first method we are going to have all the 4 variables, that is as select lines, and we are going to use the 16 cross 1 multiplexer. But so we are going to use the just second method, that is the reason, that is n-1 means 4 minus 1 3. So 3 means what, 2 cube. So finally we are going to use 8 cross 1 multiplexer for the process for this. It is very easy, simple. For the 8 cross 1 multiplexer we can simply do that. So let's see how to do that. So this is the 8 cross 1 multiplexer that I am taking. So if you observe, directly I am passing A, B, C as the select lines. So if you observe, where is the variable D? So we are going to pass variable D with the comparison of variable F. So F is our output, that the question that they are given is the F is the output. So we have to compare F and D. So in terms, the F should be represented in terms of D as input lines. So let's see how to do that. So as the representation shows, the ABC is select lines and D is input lines. So D can be represented F in the format D. So as you already saw in the first example, the same principles we are going to apply in this also. So if you are going to compare the F and D, so the first four boxes that you observe carefully. So the D is 0 1, the F also 0 1. So that is not changing. So the output F can be represented in form of D as same only. So F is equals to D. So if you observe in the for 8x1 multiplexer also, I have directly changed that as D, that is D not the first select line, that means the if you select lines as 0 0 0, if you send directly, the D not would be selected. So directly I connected as D. So if you move forward, then also you can able to find the next two columns also, that ABC is same, that is 0 0 1, that is ABC, and again is 0 0 1. You can observe that D and F is also not changing again. So F is equals to D. So the next D1 is also D only. So if you move forward again, you can observe. So the F is dominating. That is, we cannot represent the D and F because there is no relation between D and F. So directly we can represent F in terms of D, that is 0. So there is no relation. So F is equals to 0. So you can observe the third that is D2 is 0. We can simply represent. In the 8x1 multiplexer, observe I have changed also, that is 0. So the fourth term, if you observe, we have some relation between D and F. If you observe, D is 0 1, F is 1 0. So we already saw in the first example, that is the D bar. So we can represent D in terms of, sorry, F in terms of D, that is D bar. So represent the D3, that is D bar. So see the 8x1 multiplexer, I have changed it over there. So like that you can fill or the remaining table. But see the last case, when both are 1 1, the F is both are 1 1, but we do not have any relation between F and D, because D is 0 1, F is 1 1. So we cannot represent F in terms of D. So directly we are going to have F is equals to 1. So you can also see in the 8x multiplexer that I have represented D7. The last one, if you send ABC as 1 1 1, the final output would be D7. So what is our D7 in terms of D? That is 1 only. We do not have any relation. We just have the output, that is 1. I hope you understood the second method very well. So with the help of two examples, so we are going to just start the multiplexers as universal logic. So to implement all logic gates, so this requires the basic theory, or that we also already, that is very important. So I hope you understood. So let's get started for the implementation of all logic gates with the multiplexer. These are the all 7 logic gates that we are going to implement with the help of multiplexer. So let's get started with the NOT gate. So just start the NOT gate. So with the help of multiplexer. So just forgot about the NOT gate and its all things. So let's just focus on the 2x1 multiplexer. So we already discussed the basics of 2x1 multiplexer. So we can have one select line and 2 inputs and 1 output. We are very much clarity about this, but we have the output expression as S naught bar D naught plus S naught D1. I hope you know this. Then come to the NOT gate part. So if you observe the NOT gate, we have the input A and we are getting output A bar. So you are observing the truth table also. I hope you know this. So there's the play. Now you have to have some logic that you are going to pass as inputs and in the select line, so that you are going to have the output expression as A bar. I hope you are understanding. So again I will repeat. You are going to have some logic in the inputs and in the select line, so that you are going to have output as A bar, because this is the output of NOT gate. So if you observe, so you might not understand with the help of NOT gate, but further processing we can understand all the logic gates. But remember, for just NOT gate, we are going to have in the select line as A, and we are going to pass the as D0 as 1 and D1 as 0, so that you are going to see the terms that S0 as A, D0 as 1, D1 as 0, so that we can able to replace all the S0 and D0s in the output expression, and we can get the final output expression as A bar. So this is simple, that I think. So observe carefully. Or if you want more clarify about this, why you are only sending 1 0. So observe the truth table of NOT gate. What the output expressions we had? That is 1 0. That is A bar for A bar. So simply pass A bar. That's it. That is our final output expression. Because if A is 0, we are going to select D0. If A is 1, we are going to select D1. So that is the reason we are going to pass 1 0, or the output expression y is equals to A bar according to the NOT gate output. So I hope you are understanding. So if for the more if you see more examples, then you can able to understand. So now it's time to discuss the AND gate. So you can see the circuit diagram and the logic expression, that is y is equals to AB. You can also observe the truth table. I hope you know this truth table. All the first three inputs are 0. Next last output is 1 when both the inputs are 1. So you can also know the output expression. We already saw the output expression for the 2x1 multiplexer. So see this is very important. Once you understood this single AND gate, then you can able to understand all the remaining gates. So this is the logic truth table that we are formulated with the help of the logic that we have saw in the upcoming the first beginning of the video. So if you observe the truth table clearly, you can able to see the same truth table A, B, Y, but a small change. A, I am passing as select line. B, I am using with the help of Y, I am comparing B with the Y, and I am going to represent the output Y in terms of B in the input terms. So if you observe the first 4 boxes, you can able to observe in the B of Y. So Y is just 0 0. So our output would be just Y is 0, because we do not have any relation between Y and 0. Just Y is changing from 0 to 0. So that is the reason we have the output expression as Y is equals to 0. If you have any relation with B, means take the relation. So that's the second case. The second case also we will see, but Y is equals to 0 for the first one. So D naught would be 0. So I have represented in the true constant multiplexer also, you can observe over there. So if you observe the next 2 boxes, you can see a clear relation between Y and B. Both are same. So for the both conditions, Y is equals to B. So that represent in the truth table, means 2x1 multiplexer also, you can observe there that D1 is equals to B. So from the output expression of the 2x1 multiplexer, that is S naught bar D naught plus S naught D1. So change all the values, that is S naught A, D naught 0, D1 B. So put the values in that, and you are going to obtain the output expression as Y is equals to AB. So let's move forward. If you observe, this is the OR gate. So I hope you know the OR gate, the truth table, that is the first condition is 0 for both of the inputs is 0. Next 3 cases would be 1. So let's get the output expression with the help of the multiplexer also. Let's see that. So if you observe clearly, that I have said in the previous example and AND gate also, the same thing that we are going to follow in this also. So if you observe the comparison between B and Y, so A is the select line, leave that. So if you compare between B and Y, so if you observe for the first 2 conditions, both are same. So Y is equals to B. So then D naught is equals to B. For the next conditions, if you observe, there is no relation. So simply Y is equals to 1. Y is changing from 1 to 1. So simply output Y is equals to 1. I am going to take D1 as 1. You can also observe there. So according to the output expression, that Y, how we will write A bar into B plus that A into 1, that is the output expression, right? So as we are changing that all values. So after that A bar B plus A, that we can represent with the A bar plus A plus B plus A. So this is the representation of distribution law. So if you don't know how to represent this distributive law, I am giving the video in the description box, check it out. So that is Boolean algebra, that is simply I can say. So A bar plus A is equals to 1, simply output expression would be Y is equals to A plus B. Then the next one is NOR gate. If you consider the NOR gate, it's what? Just opposite of the OR gate. So that is A plus B whole bar. If you consider the truth table, so the whole magic will be considered in the truth table only. So truth table is main. If you consider the truth table, that is the outputs are 1 0 0. So for the implementation of NOR gate with the multiplexer, you can see there. So as the previous ones only, you are going to have the first truth table. That first 2 conditions we have to compare the B and Y. If you compare both of them, you can also observe a relation between them. That is Y is equals to B bar. Next to them, if you compare, we do not have any relation. So but Y is changing from 0 to 0. So that is the reason we have to Y is equals to 0. So that Y is equals to 0 is our D1 and Y is equals to B bar is our D naught. So according to the output expression of multiplexer, we are going to replace all the variables over there, and we are going to get the final output as A bar dot B bar. So if you apply De Morgan's law, we are going to have the final output expression as A plus B whole bar. I hope you understood this. So we already completed one universal gate, that is NOR gate. So this is the second universal gate implementation with multiplexers, that is the NAND gate. So if you observe the truth table also, it is very known familiar one, that is exactly opposite of AND gate. So A dot B whole bar, that is 1110. So in the same way, we are going to have the truth table, the comparison format of B and Y. So A is select line as usual. So if you observe, if you compare B and Y for the first 2 rows or M naught M1 min terms, so there is no relation between B and Y, but Y is changing from 1 to 1. So we are considering that output expression in terms of B as nothing, that is why the reason is Y is equals to 1. So d naught is 1 and y is equals to b bar. You can also simply observe that, because when b is equals to 0, y is 1, b is 0. So we also know the true constant multiplexer output expression. So put the variables over inside that expression. So after that we are going to have a bar plus a b bar. So again apply the distributive law, that a dot b bar will be distributed to a bar. So we are going to have like that. So after that we also know a plus a bar is 1. So finally we are going to have a bar plus b bar. Apply again De Morgan's law. That is our final output expression of NAND gate, a dot b whole bar. So the next important gate is XOR gate. So mainly the XOR gate is important because this might be asked in your university exams or in the main exams like gate exam. This kind of exams they might ask. So let's see the XOR gate implementation with the multiplexer, 2x1 multiplexer. So already I hope you know the truth table of the XOR gate. So this is the truth table. So that is when both of the inputs are same, the output would be 0. When both of the inputs are different, the output would be 1. Again we have to follow the same procedure. We have to compare b and y, and a is again the select line. If you observe, we can see that the b and y are same, so y is equals to b again. If you observe the next one, that is y is equals to b bar simply. So again replace the d0 and d1 over there, and you can apply this directly. You can get this a XOR b, that is a bar b plus a b bar. So the last and final gate of this whole 7 gates is that XNOR gate. So this is just exactly opposite of the XNOR gate. So you can represent the thing that is a with the just opposite, means we can represent the a XOR b whole bar, or you can represent like a bar b bar plus a b b, or you can simply represent with a symbol like dot outside a circle. So I hope you know the truth table also, just exactly opposite of the truth table of XOR gate, that is 1001. Again follow the same procedure. You are going to get y is equals to b bar, and again y is equals to b. So put in the 2x1 multiplex. So in the output expression of y, 2x1 multiplex, so put those variables and you are going to get y is equals to a XNOR b, that is a bar b bar plus a b. So this is not still over. We can implement any of the logic circuit that we want. So we can implement half adder, full adder, half subtractor, full subtractor, any of the things. So these things we will see in upcoming video. So I hope you understood this video. So thanks for watching up to now.